Hello everyone, my name is Dennis Wizard, and today I will be briefly talking about our ACL 2026 paper, Crosscoding Through Time. This is a joint work with Aaron Muller from Boston University and my advisor Antoine Bosselieu from EPFL. In this paper, we wanted to understand how LLMs build up their representation of language during pre-training. While we know that early pre-training is where LLMs improve their linguistic abilities, we don't exactly know how this happens. We lack the understanding of which features emerge or fade during this process. Let's take as an example our case study task, subject-verb agreement. The goal of the task is for the model to generate the right verb completion such that it agrees with the subject. To measure the model's progression over training in this task, we can trace some metric like accuracy and point where the model got better at subject-verb agreement. But exactly which features make this 4B token checkpoint, for example, better than earlier ones, or whether any early features persist all the way to the end of pre-training is unknown. So, metrics tell us when LLMs improve behaviorally, but they do not tell us how they change internally. What are the features that could be driving these new behaviors? For example, maybe early on, the model fails because it is distracted by a feature that detects plural inanimate objects, putting the importance more on the noun mats. Later, it might improve because it relies more on a feature that detects nouns before prepositions. So what we really want is a concept-level, human-interpretable description of the feature change, what the model is acquiring or losing during pre-training. That's the gap we wanted to close. So how can we trace the evolution? Our secret recipe has three parts. First, to be able to compare features across checkpoints, we learn a joint feature space. Second, we quantify which features are causally important at each task. Finally, we rank and annotate the top features to give each feature a human interpretable concept. To learn the joint feature space, we use sparse crosscoders, which can learn a dictionary of features across multiple sources of activations. This is what allows us to make a direct comparison of each feature across training. Note that we learn these crosscoders for critical checkpoints rather than all checkpoints at once. To measure importance, we look at the causal effect of ablating the particular feature. This is called an indirect effect, or IE, and we calculate it for each feature and each checkpoint. But IE alone does not tell us whether that effect is large relative to the same feature's effect at other checkpoints. So we introduce relative IE. For each feature, we take its absolute indirect effect at each checkpoint, and we normalize it by the feature's total absolute IE across all selected checkpoints. Here is what relative IE can look like for most important features across the three task-critical checkpoints we mentioned early on. Each point is a feature, and its position shows us where most of that feature's causal effect is concentrated relative to all three checkpoints. So RelIE lets us understand how concepts fade, strengthen, or stick around during pre-training. This is the part that standard accuracy curves couldn't tell us. Finally, to turn feature IDs into something interpretable, we annotate the top causal features using their top activating example. This is a standard interpretation step, so we'll keep it brief and refer viewers to the paper for details. Now that we can trace and annotate features, we ask two questions. How do features change during training? Which ones emerge, strengthen, or fade? And do multilingual models consolidate features across languages, or are they kept separately for each language? For the first research question, we look at the most positive and negative causal features across the three checkpoints. What we see is a clear shift in the kind of features that matter. Early in the training, many important features are quite surface level, but later they become more grammatical and abstract. We see detectors for prepositions, nominalizations, and many more high-level concepts. So the takeaway is that the model is not simply adding more capacity over time, it is rebuilding the mechanism. Token-level features fade, while more grammatical features strengthen. The previous slide showed that the type of features change over training. But we also want to quantify how interpretable features distribute across these three critical checkpoints. While there are some core features that are shared among all, meaning they persist throughout pre-training, we also see that most features are primarily shared between the 4B and 286B token checkpoints. These two checkpoints, despite sharing performance, also have many checkpoint-specific features, meaning that accuracy plateau does not always imply a representation plateau. For the second research question, we applied the same pipeline to a multilingual model and subject-verb agreement dataset. We ranked the top causal features across three checkpoints for English and French, and then we grouped them by RelIE to see how they change over time. We noticed that early features can be language-specific, like an English-only detector for that. But later, we see that the English task is requiring more cross-lingual features, such as a relative pronoun detector covering Arabic, English, French, Portuguese, and Spanish forms. So not every feature becomes universal, but related linguistic functions increasingly consolidate into shared cross-lingual features. To quantify this consolidation, we measure the overlap between each language's top IE features. We first observe that the overlap is not monotonic. It can decrease mid-training, but by the end of pre-training, it increases substantially, especially for languages that share script and subject-verb agreement systems. This suggests that multilingual consolidation is gradual and uneven. The model starts with more language-specific features and later builds more shared grammatical features, though, for example, Hindi shows less sharing. So to summarize, in this paper we propose a way to trace how linguistic representations evolve during pre-training. We do so thanks to learning a shared feature space across checkpoints. We propose a way to rank when features causally matter during training. And finally, we analyze which features emerge, persist, or fade. What we find is that behavioral plateaus hide internal change, while surface features fade, grammatical features strengthen, and, and interestingly, multilingual features consolidate, although this is done quite unevenly. Thank you for listening, and you can read more in the paper at the link shown here, and I hope to see you at ACL 2026.